Hi, everybody. Welcome to my talk titled Lambda All the Things. My name is Braden Ganetsky, and they have given me a title card here, but I would like to present my own title card, this one right here.
Thank you.
So this is Lambda All the Things. A little bit about myself before we get started. I am Canadian. I have a mechanical engineering degree. I like twisty puzzles. If you think this kind of thing is cool, talk to me later about it. I've been working professionally in C++ for 4 years. I've been on the C++ committee since 2023. And for the past 6 months or so, I've been running the Winnipeg C++ developers. This is my local user group, trying to get that off the ground. It's been an exciting experience. If there is anybody in the future watching this video who is in or around Winnipeg, contact me. I'd love to have you at the meetup. So this talk is all about lambdas. Lambdas were introduced in C++ 11, and they are typically on the cutting edge of C++ features, meaning that there are often things that are in lambdas that come in earlier C++ versions than when they are in the rest of the language. I based the name of this talk off of Ben Dean and Jason Turner's famous Const Expert All the Things, where in that talk, they tried to answer a question. And the question they asked was, how much are we able to do at compile time with Const Expert? And so in a similar vein, I am asking a question. How much can we do without structs or classes, without unions, and without functions? How much can we do? So some of you might be sitting here and thinking, oh, I immediately think of the structured interpretation of computer programs, right? I'm just going to build everything out of closure types, and I'll wrap closures and more closures, and I'll turn this into a Lisp dialect in C++. And I'm not doing that. In fact, there are actually 2 talks this week about building stuff up from lambdas. Steve Downey is talking about building streams out of hot air. So doing also, we originally thought kind of a similar talk to each other. Now we know they are going to be different, but that's only after discussing with each other. He's giving this on Friday. So I am not going in that direction of building things from the ground up, kind of like structure and interpretation of computer programs. Instead, what I'll be doing is I want to see how much of the standard library we're able to implement with minimal classes, structs, unions, and functions in C++ 23, and basically to determine the number of rule breaks that we're going to need. And I'm defining a rule break to be every time we need to define a class, a struct, a union, or a function. That's going to be a rule break. But the caveat is I want to maintain C++'s semantics. And that's why I can't go the whole SICP route, because then there'd be a lot of things that are semantically inherent in C++ that I would break completely by doing it like that. So I want to maintain C++'s semantics that we all know and love. Some of us just know. But this talk is basically at its core a thought experiment. We just want to try and see how much we're able to do. But using the scientific method. And by that I mean an answer of no is a valid answer. So if it turns out that there's something we're not able to do with lambdas, that's the answer, and that's how it goes. But it will be a fun challenge. We will be testing the limits of lambdas. I have had this talk described to me as a 90-minute lightning talk, and in that, I think the most core element is that it's full of code you shouldn't write. But it is an exploratory talk, and it will push the boundaries of what we're able to do in the C++ language. And the way the talk is going to go is first I'll talk about, briefly, the history of C++ lambdas. I'll talk about type traits and utilities, basically how to implement these sorts of things using only lambdas. Then I'll go through a class by example. I'll talk about unique pointer and go through all the various different things that will build up to that. And then at the end of the talk, I'll talk about some more features that we might want that are outside of unique pointer. So without further ado, here's the history of C++ lambdas. A lot of you in this room know this very well, so this will just be a refresher, especially the early parts. So the early parts is C++ 11, where we were able to capture variables from the enclosing scope by copy or by reference, and we could do this variadically. We could capture things by default. We could do a default capture of things by copy or by reference using the equals or the ampersand. We're able to capture the enclosing object by reference. That's very important. And a non-generic call operator. This is const by default, a feature that is different than the rest of the language. And very importantly, optionally deduced return type. Like you can write a function without writing the return type in C++ 11, as long as it's a lambda. So that's pretty cool. here is about as C++11y as a lambda as I'm able to come up with. So there's a struct here. It has two data members, and it has a function template here called foo. It takes an int, it takes an L value pack, and then inside of it, it has a lambda that captures x by value. It captures the enclosing object by reference, and it captures the pack of L values also by reference. It takes an int, and then inside we are just doing something. We don't know what that thing is. It doesn't particularly matter. And then we're just returning lambda of the data member y from this function. And this is about as many of the C++11 features as I could think to fit in one single example here. In C++14, we got a few new additions. In the lambda, we could get the generic call operator, which of course made lambdas a lot more usable in a lot more cases, like algorithms, for example. We can also capture by copy or by reference now with an initializer. This was not possible before C++11. So in that way, C++14 added some sorely needed features to the C++11 lambdas. And for a lot of us, I think when we think of the default base level lambdas, we're really thinking of the C++14 lambdas. That's when they really shine. And doing this actually allows capture by move or by const reference, which really is not possible in C++11. We can also have default arguments to the call operator. I don't know who has used that here in a lambda, but in doing this project, I actually have. And we can return lambdas from a function. Now, that's not specifically a property of lambdas, but that is a property of the language that now allows us to interface with lambdas in a better way. So I'm going to take this C++11 lambda example and turn it into a C++14 example. I'll do a few things. First, instead of taking int, I'm going to take auto. And the reason being, this is C++14, so we'll take auto. I also would like to add a default parameter here. This default parameter is going to be w equal to 7. Again, this is now a thing we can do in C++14. As well, I don't want to capture x and call it x. I want to capture x but rename it to value. And now we can do that in C++14. And then instead of returning lambda of y from this function, I'm just going to return the lambda itself. Because let's say the lambda does some computationally intensive thing, and I don't want to do this necessarily immediately. Maybe I don't want to do it at all. So I'll just return the lambda, and we'll maybe call it later. So that's the C++14 example. In C++17, we got the const expert call operator, actually by default. So if you leave out const expert from the call operator, it still is a const expert capable call operator, as long as the body is as well. We can capture the enclosing object by copy as well. So you might have noticed a problem actually in my previous example. And I'll get to that in a second. But first I'm going to add const expert here because I want to specify. This is, you can run this at compile time. I mean, the rest of it's not compile time capable, but this is. But really what I need to do is capture this by copy. And the reason being that this actually creates a potential lifetime issue. Because inside the lambda, I am calling a data member of the enclosing object. Where I write in source code the letter z, the data member, it's actually this arrow, z. That's really what we're calling. And if the enclosing object goes out of scope before we call the lambda, then we have a dangling reference, and that's an issue. And so if we capture by copy, then we don't have that lifetime issue anymore, and that solves any of those potential pitfalls. So that's quite nice. C++20 gave us a whole slew of features. These are very exciting. Lambdas are allowed in unevaluated contexts. Lambdas that are captureless can be non-type template parameters. We can have a const eval call operator now. We can have an explicit template parameter list. We can constrain the template parameter list or the call operator. And we can capture a pack by copy or by reference with an initializer. And I'll show off a few of these here with some examples.
And you can default construct them.
Sorry?
You can default construct them.
You can default construct what?
A lambda. Lambda object. If it doesn't have a lambda capture, you can default construct it.
I didn't know that was a C++20 feature. I assumed that was from the beginning.
No,
okay, good catch.
20.
Okay. Cool. No, that's great to know. All right. And here's a few of these things. Foo here is just a tag type. It's just the decal type of an empty lambda. That's a lambda in an unevaluated context. Here is another lambda in an unevaluated context. We can do that. Here we can create a struct template that takes a non-type template parameter, and we can pass it a lambda as a non-type template parameter. That's pretty nice. Let's say I have a constraint in my code where I need to add two numbers together, but only when it's at compile time. So let's do that. We can only add these numbers at compile time. Great. Const eval call operator. Here we have an explicit template parameter list. We have class t. We have a constraint on that template parameter. We have requires stood integral of t. In the actual parameter list of the call operator, we have t as a template parameter. But there is a second template parameter as well. The type of u is a template parameter, but it's a template parameter that has no name. And so the full template parameter list is both the explicit and the implicit stitched together. And then we have a trailing requires clause, just making sure that t plus u is a valid expression. And this is also something we can do in C++20. But by far, my favorite C++20 Lambda feature is an example from Daisy Holman's What You Can Learn from Being Too Cute. It's a great piece of code here and a great talk. You should watch this talk. Basically, she writes a lot of code that she says you shouldn't write. But I would argue this is a piece of code that is really nice to write. And this is directly verbatim from her talk. This is a function called enumeratePack that takes in a function f and a pack of arguments. And what we do is we create a lambda. This lambda has an explicit template parameter list of size t's, and then we match those size t's, or we're able to match on those size t's from the index sequence that we get passed. We pass the index sequence immediately inline, so this is an immediately invoked lambda. And inside the body of the lambda, we just call this function with each index and each argument pairwise. So we are able to enumerate this pack without introducing another identifier. That's pretty cool. Because before C++20, the way we did this is with an impl function, right? You need to define some other function, either underscore impl or in a detail namespace or some other way of hiding the identifier. But in C++20, you can write this code without worrying about it. You don't have to worry about whether your user is going to be able to access this thing. I know, in the top example, my user cannot access the inner thing because it is immediately invoked. Perfect. But before C++20, we had to create this impl function and then call it from the actual function. It creates a new symbol. I just don't want to do that. In C++23, there's a few new features. We have attributes on the call operator now. We're able to drop the empty parentheses in, I think, all cases. I may get a correction here, but I think it's all cases we can now drop the empty parentheses. We can mark the call operator as static, and we can have an explicit object parameter. People often call this by the name of the paper, deducing this. We can do that in C++23 as well. So here's a little bit of that. This has a C++20 explicit template parameter list, as well as a no return attribute on the call operator because this lambda can never return. And there's also the static annotation just showing that this pointer is never needed inside the body of this lambda. This is an example from CPP reference to find the nth Fibonacci number. It's called 3 because it's the third one on that page. And this shows how to do it in C++23. We take a thisAutoSelf, and then we're able to use that inside of the body, and we're able to recurse calling self with the remaining arguments. And so this makes writing recursive lambdas a lot easier than before. Before, what we needed to do looked something like this, which is almost the same. However, we need to call self with self as the first argument. OK, and that's where we're at today with lambdas. We'll see what's coming down the pipeline in the future. But for now, I'll talk about how to implement type traits and utilities, or at least how I have determined how to implement type traits and utilities using only lambdas, let's say. Here's something I need everyone to remember, though. The type of a lambda expression is a unique, unnamed, non-union class type. This is very important. Every time you create a lambda, it is a unique type. So with that in mind, the way the type traits and utilities section is going to work, we'll start with integral constant, then we'll talk about some querying traits like isSame. Then we'll implement stood type identity, which is a very important building block in implementing a lot of the other traits. We'll implement some casting functions, and then we'll talk about overloading. So for integral constant, the first one we're doing, remember, no structs. OK, so the way that I implemented integral constant, it's quite simple. It wasn't simple when I started, but looking back, it's quite simple. I'm just creating a lambda. It takes a template parameter list of class t and then tv. It's the same template parameter list as stood integral constant. And it's just a lambda that returns a v. And then integral constant itself will be the type of that lambda, the closure type. And so we need to test to make sure that this works. If we instantiate, or if we grab an alias for integral constant of int comma 0 2 different times, is this going to be the same type, or will it be 2 different types? What if we grab int comma 1? What if we grab long comma 0? I'm sorry? Yeah? No, you had something to say. Okay.
No, keep going. Great.
Okay. Okay. So the answer is A and B are the same type. A and C are different types, and A and D are different types. And I just had this static assert just to make sure that we are on the right track and that we don't fall apart right at the beginning. So this does work. Yeah.
Now, can you go back one slide and just remind me again what the static was there?
Yeah.
Specifically for?
Sure. That's you are annotating the call operator of the closure type with static, meaning that when you use that call operator, it's not a member function, it's a static member function. And in doing that, internally, this pointer just doesn't get passed. So, yeah.
And can you explain how you're using auto? Is that
Yes.
decay copy?
Yes, that's decay copy. That's a new feature in C++23. The reason I do that is because, and this took me an embarrassingly long amount of time to debug originally, without that auto, I would try to... It's const, yeah. And it really tripped me up because I spent multiple hours, an embarrassingly long amount of time, and then after that I thought, no, I'm just auto-decaying everything so that I can get rid of const and things will be easier that way. So that's the feature I'm using. It's a C++23 feature there. So just making sure that these are the same, and if I grab two aliases for the same template parameters, that will give me the same lambda 2 different times. I just need to make sure that's the case. I'm also going to grab bool constant and true type and false type, but now that I've done that, hey, that's stood integral constant. Cool. That's our first win. There will be more, I promise. We'll talk about the querying traits here. The first one I want to implement is same. Now, the naive way of doing it is using a struct, but if you know C++14 and beyond, you can do this with a variable template. So you can create the primary template for this variable template is same v equals false. And then the partial specialization, when you give it the same type twice, this will be equal to true. And so you don't have to create a struct in order to create is_same. You can write the struct from is_same. And so this is how all the standard libraries do it. But why don't the standard libraries do it like on the right side? Does anyone know if the right side is legal C++? Or at least as per the standard, is it legal to define is_same in this way?
No, because it can't be a type alias of bool constant. It has to be its own symbol.
Yeah, it has to be its own symbol. So each of these templates shall be a CPP17 binary type trait with a base characteristic of true type, yada yada. But the important part is to see what CPP17 binary type trait is. Just highlighting the important bits, it shall be a class template that publicly and unambiguously is derived from integral constant. So it needs to be its own type, but it needs to be convertible to either true type or false type. And the reason being that this is used in a lot of code for dispatching. Before we had ifconstexpr, I know, could you imagine a time before ifconstexpr? You would dispatch to function implementations like this. So you might have a foo_impl that takes a set of parameters and then a true type at the end, and then a different foo_impl that takes a set of parameters and a false type at the end. Right, and then you have this foo that dispatches to foo_impl, or detail foo, or whatever you want to call it, but it dispatches passing is_same. But now, is_same is not itself a true type or a false type. It is its own type derived from true type or false type. So in this case, the behavior that we actually need, the semantics that we need to maintain, is base class slicing. That's what we really need in this case. But unfortunately, with lambdas, there are no implicit conversions. Yes, you can convert to a function pointer, but that isn't very useful in a lot of cases, and that wouldn't really help us here. So we do need implicit conversion, and we will not get implicit conversion. And because of that, I'm implementing it using an alias. So we still maintain the same semantics that we get in standard C++. I'm also going to implement the same as concept. So I have same as impl being is_same, and then I have same as being a subsumption of same as impl of t comma u, and same as impl of u comma t. That's just needed for, I think, commutativity of the parameters. But if we've implemented the trait, the associated concept should be pretty well close. So I'm just going to show the _v traits for the rest of this here. So once we've done that, I'll just show a few others. Is_l value reference is about as complex as is_same, which is to say it isn't. Is_const is also about as complex. Is_pointer is a little bit more complex just because there are more specializations, but it's really not that bad. And then conjunction is really nice in C++17. It's a little bit ugly before that, but in C++17, this is quite nice. And that's our querying traits. So all of them are more or less as implementable as they are in a regular standard library. Now let's talk about type identity. Naively, this is how you would implement type identity. Is this the right way to implement type identity?
That
Yes or no?
doesn't make a non-deduced context.
It doesn't make a non-deduced context. So this is wrong. Because from CPP reference, and I'll explain what a non-deduced context is here, we have these two functions, foo and bar. Foo takes a t and then another t. Bar takes a t and, well, also another t, right? But it's laundered through this machinery. And that makes it have different behavior. And I don't mean launder like stood launder. So that means that here, when you call foo of a double and an int, it's not able to deduce the type because the compiler does not determine which of these types is able to be the type of the template parameter. But for bar, we've created a non-deduced context on the b parameter so that when we pass 4.2, 1, it deduces as bar of double. If we were to put type identity on the other parameter, it would deduce as bar of int. And this is called a non-deduced context. That's what it creates. It's not, yes?
No, just to make a small plug here, but on my talk on Monday, I explained non-deduced context in a lot of detail if anyone wants to watch it.
Oh, okay, great. Well, people should watch that talk then. So type identity f, this is the first thing that I tried. I wanted to make this lambda that's effectively just a function declaration. It doesn't have a body, but it returns a t. But that doesn't matter because I'm just using it like a declaration. And then I'm going to implement type identity underscore t as the decl type of calling that lambda. And this doesn't work. It doesn't create a non-deduced context. Okay, let's try a few more things. Let's put the template parameter on the call operator. And then to make type identity underscore t, we have to do some other syntax. But, you know, it's basically the same thing semantically. Doesn't work. Okay, but if you do both, it turns out if you write type identity underscore t and then also type identity like this, yeah, it works. This actually does create a non-deduced context. And again, I'm using that decl type auto, so I'm auto-decaying the type of the lambda. I just want to remove the const. Instead of using a trait for that, I'm just using pure C++ code, no library code there. So now this will work in this example from CPP reference. Yes?
Is that a typo? The last type identity f, should that be type identity t?
No, that should be type identity f. So it's taking the type of the lambda. Okay. Yeah, so type identity underscore t is grabbing the type of what happens when you call the lambda, but type identity is the type of the closure object itself.
Okay.
Yeah.
Never mind.
So that actually works. Okay, great. We have type identity. So now let's use type identity as a building block to build a few more things. Let's create add const. Add const will use type identity in order to be implemented. And this actually, even as per the standard library, even in the standard, this is a legal implementation of add const. Assuming type identity is also implemented legally, this is a legal implementation of add const. And add const underscore t is also similarly, just like this, type identity underscore t of const t. And so then let's just, just making sure it works, of course, let's static assert that add const underscore t of int is going to be equal to int const. Yeah, does anyone disagree? Does anyone think it should be const int instead? No. No, does anyone disagree that this should be a constant int?
It seems obvious, yes.
It's int.
Okay.
I did something wrong. Does anyone know what I did wrong?
Well, you're decaying, man.
I'm decaying.
Oh. It's const qualifier on the return type.
Yep. Yeah, so that's the problem here. In order to create, in order to create this non-deduced context, I'm calling a function. I'm using a call operator. We're evaluating a function and then grabbing the return type of that function. It decays away the const. It decays away volatile. It decays away array types. We get rid of all that stuff. So in order to craft this non-deduced context, I made type identity work incorrectly. Do you know what does work correctly? The naive way. But it works correctly in the sense that it gives the right thing. But it doesn't work in a non-deduced context. And these are both things that we need to rectify. We need to make sure that both of these things work for type identity. I didn't even bother implementing whatever type identity would be. You have to wrap it in something, but because this doesn't create a non-deduced context, I don't think that's valuable. But we've run across another Lambda restriction, which is that we cannot have a member type def. And that's what creates that non-deduced context, right? We create a struct template. We create a struct template that has a member alias. And because struct templates can be specialized, well, the compiler doesn't... Is that not how it works? I saw you shaking your head.
So can you repeat that? Sorry.
So I was saying that the way that this works is the struct template, because it's able to be specialized later, the compiler can't see through the type identity underscore.
Yeah, that's one reason, right?
Okay.
Like you don't in C++, you don't instantiate class templates with dependent arguments, because if there was specialization, explicit specialization, like for example int, you wouldn't know like which one to pick, right? So that's one reason dependent type lookup you cannot resolve it.
Yeah, so the compiler's unable to see through it when it is an alias of a struct template. And I think this is the best we can do in C++23. I have not been able to come up with a better way, and that's a rule break.
So there are other ways to other circumstances that create non-deduced context.
Okay.
You can read it at the study, but one that you came across before was one of them, like decal type. Like you don't deduce through decal type. So that's one.
Right. So that did create the non-deduced context, but it did end up meaning that it gives the it gives an incorrect type. And I wasn't able to find anything that does both of those things. I'd like to at some point, but I did find something. It is in C++, in standard C++ 26. So if you want to go to this Godbolt link, you can, assuming P2996 gets in, you can grab a Lambda that returns the reflection of your type, and then you can just reify that reflection, and that does work. And it has both of the things that we need. It creates the non-deduced context, and it also works for all types. So the problem is we don't have that yet. So I did have to do a rule break. And so I just have this alias that I've created called typeof that, like, if we have reflection, do the reflection thing. But if we don't have reflection, then use a member alias. And that's just what we have to do for now. So we ran into our first unavoidable rule break. Growth opportunity. So type identity must be a struct template before C++26. Otherwise, it doesn't work. You can't get the same semantics. But now that we have it, we can implement addConst. And now addConst is trivial, right? Because we can just implement it as an alias for type identity. Similar with addVolatile. These ones are quite easy. RemoveConst is a little bit more complicated because it requires a variable template. So you need the primary template here, just being type identity of whatever type you pass. But in the case that you give it a const t, well, then it'll strip off the const. And now I'm just going to put it through some other machinery. I'm going to say removeConst is this whole decal type of auto thing that I've been doing the whole time. I'm just grabbing the type of the Lambda. And then removeConst underscore t, I'm now using that type of alias so that I can grab the internal type properly, both in C++23 and eventually when we get reflection. So that's removeConst. There's other ones that work similarly to this, where you need the primary template and the partial specialization. One of them is enable if. Implementing enable if, you can do this with just setting the primary to 0. I do that because it's kind of equivalent to just a declaration. 0 is not a Lambda. It has no call operator. There's nothing you can do with it. It's just an int. So it's equivalent to a declaration. And then my partial specialization in the case of true is going to be type identity of t. And then again, I will pass it through this same machinery of decal type of auto, just grabbing the type of this Lambda. And then enable if underscore t, again through the same thing. All of these traits are implemented similarly. Conditional is another one. The primary just returns type identity of f, and then the partial specialization returns type identity of t as long as the bool is true. One more that I'm going to show here, actually two more that I'm going to show, but this one builds up to the other one. Add R-value reference impl. The primary is just going to be type identity of T. But then in the case that tref names a valid type using sphere, I'm just going to return type identity of tref. And I'm going to use that. I'm putting it through the same machinery. You can imagine I don't have that shown here. But I'm going to use that to implement declval. And declval, this actually works the same way that std declval works. It needs a template parameter on the outside because you need to pass declval an explicit template parameter. And then internally, it also needs a generic call operator. So we need a class u equals t. And then it's just going to return add r-value reference underscore t. And we have the static assert false. This is a new feature as of the C++23 standard, where you can just static assert false directly. But I heard recently that it was backported to C++11. Someone might correct me there. I think this is going to be available in C++11. Is that right?
I don't think that we do like a feature SDI. It just so happens the client does, probably other compilers will do. They will apply that as an extension to the past just because we don't think that's going to cause any issues or breakages, right? But I don't think that's really something that it can be decided in the standard even.
I thought it was an official DR all the way back to 11. I'm not sure. But regardless, you're able to do this. I'm working in 23 anyway. Now that we have declval, the last trait I'll show is decay. And decay is really easy in C++23 because of the auto decay. So I can just take the decl type of the auto decay of the declval. Oh, yes, I didn't see your question.
So for declval, are you missing like decay for you before adding r-value reference T?
Not that I know of.
It would collapse, right?
Yeah, I think so.
And that's what we need. Yes.
Sorry, yeah, I think this is fine. I have extensive testing just to ensure that it returns the same thing that the standard one does. Yeah. No, but that is a good point. So implementing decay is very easy because we have this auto decay. So that's that's easy in C++23. Now we'll get to the casting functions. I already showed declval. I'm calling that a casting function. We're casting to nothing, but we're casting to PR value. Sorry, no, we are not casting to PR value. I don't know what the proper terminology is. But I'm thinking of it like a casting function. What does cast to PR value is move, which is just a direct translation from the standard implementation, which is quite easy because using a lambda as just a regular function is quite easy. So this works the same way that std move works.
Surprise.
Yeah, exactly. As const works the same way that std as const works. A little bit harder is going to be forward. And the reason forward will be hard is because there are two overloads. There's the L value and the R value overload. So what we could do is have forward L value and then forward R value. And we need a static assert in forward R value. But we could have these two, and then we could come up with some way to unify these into a single thing called forward. But I'm going to sidestep that problem, and I'm just going to implement it as one function. And this is doable. So this does work the same way that std forward works. It takes a forwarding parameter as its argument. It returns a tref. It requires that you can static cast to tref, and then the static assert is updated accordingly. But this does work the same way that std forward works. And so I'm sidestepping the overloading problem. We'll get back to that later. Forward like is also quite simple. I just copied and pasted this implementation from CPP reference and then turned the function stuff into Lambda stuff. And otherwise, it works the same. OK, I said we'd talk about overloading later. It is now later. Let's talk about overloading. So the normal way of implementing an overload set that you can do with lambdas is doing something like this. There is no standard overloaded or standard overload yet. Or maybe there won't be, I don't know, but there isn't one currently. And the way that this works is you inherit from all the f's that you were passed, and then you use the operator parens. OK, I want to implement something like this, but without structs. First, I'm going to need this concept invocable. This is not how invocable looks in the regular standard library, and that's because in the regular standard library, there are member pointers. But in my setup here, there are no member pointers. Yes, the operator parens on a lambda is a member pointer and it can be used, but not in capturing lambdas, and most of the lambdas that we'll be using are capturing lambdas. And so I'm just assuming that every time we want to invoke something, we are going to use the call operator to invoke something. And it's served me pretty well through all of this. To implement overloaded, I'm going to write some pseudocode first, and I'll set this up little bit by little bit. It's going to be a single variable, not a variable template. It will take a pack of values. They will all be f's. And then I want to return a lambda that calls one of the f's.
Enable it.
Sorry?
Enable it.
No, not enable if. So the way that I'm doing this, first I'll create some more scaffolding. I'll say, okay, if all of my types are empty, then I want a captureless lambda. If they are not empty, then I need to capture them because I don't know what's in them. But I just, if they are captureless, I want the result to be captureless. It makes things a lot easier. And so I'll make some room for this. And I will say, in the captureless case, I want to create a lambda here. It takes a pack of arguments. And we ensure that at least one of the f's is invocable on this pack of args. And we return decal type auto, because I have no idea what's going to come out of this. It's the most generic thing I can do in this case. One of the few cases where decal type auto is required. I'll do a similar thing for the capturing case, but of course I will be capturing. And so the difference here is that I'm capturing f's as a pack capture with an initializer with a move of f's. But otherwise, it's almost exactly the same. Inside of these lambdas, I want to grab the first f that is invocable for this pack of arguments. And then I want to use that f and call those arguments or call the f with those arguments. And I'll write first invocable for somewhere else. So this will be the setup of overloaded. Now we just need to implement first invocable for. Basically, the function that is going to decide which of the invocables we use. It is a function that, in a way, takes two different packs, right? It takes the pack of arguments and it takes the pack of f's. And so that means that it needs to be a variable template that has a template call operator with a pack of args. And so it'll take the pack of args on the outside, and it'll take the pack of f's on the inside of the call operator. It will take the first f and then the remaining f's, because this will be a recursive lambda. And so I'll use this, I'll use an explicit object parameter to make this lambda recursive. And the way that I'll write this is to say, if the first f is invocable with these arguments, then return the first f, because that's the one that we want. Otherwise, just recurse until we find the first f that is invocable with these arguments. And with that, we have an overload set. So let's test it. Let's say that we have this f1 that adds, yes?
So on slide 87, I think it's 87.
Oh, God. Yeah?
When you...
Oh, no. Yeah.
No, it's back.
Back?
It's the slide before this one.
Okay.
Without transitions. Yeah. When you move the f's into your capture,
yeah,
how do you preserve the value category qualifiers on the lambda call operators? Like if you pass in lambdas which are only callable with like a const ref or an r-value ref through introducing this.
Yeah, that's done by... I don't. You're right, actually. That is an error here. You're right. So, okay. Instead of these two lambdas, the ones, how do I just, there's so many lambdas and lambdas. How do I describe this?
First of, okay, but you have args.
No, so everywhere where it says args ref args, it should first say this self ref self. And then, like, in order to preserve the value category. Actually, no, maybe only in the second.
But it's more code. Yeah.
It's more code. Regardless, it's more code. I'm not going to code up here while I'm speaking. But yeah, no, that is a good point. It doesn't preserve the value category properly. So that is a case that I missed. But the case that I didn't miss is, here I have a function that adds an int to a double. Here I have a function that tells you how many parameters I gave to it. And then here I have a function that is the union of those two things. And so I have this fn. If I call fn of 3, 4, what'll it give me?
2.
You say 2? Does anyone disagree?
It'll give you 2.
So you call it a root of 5, right? Yeah. Because it takes the first matching function. That's the first matching function. That's the first one.
Oh,
It does
No,
not
it
take the
doesn't take the
first
first
matching
one.
function.
not
It
yet.
has to rank them.
Yeah, so this, the way the compiler decides which overload it wants is the
Oh.
best function. And in this
one
case,
ranks it. Sorry.
yeah, and in
this
this
one, yeah.
case, it determines the best function because using F2 does not require any conversions, but using F1 requires a conversion. And so obviously F2 is a better match. Right. If I do it in the way that I have written this overload set, I pass the first function with an x plus y, the second function with a size of t's. Fn of 3, 4 gives
5, 7. I can't do math.
7. Yeah. Yeah, no, it's not the Pythagorean theorem. It's
That's crazy.
So it gives 7. So it gives what you might argue is the wrong thing. But it's not really wrong because I constructed it from scratch to do exactly this. Like it is doing the thing that I told it to do, right? So the problem is we have another restriction. We don't have any compiler selected overloading. And we may want that. I have found in every case that I've needed, you can emulate the thing on the left-hand side by changing what happens on the right-hand side. And the way that I did that is by constraining this function. I turned it into, this lambda has a generic call operator where I actually constrain these values to same as int and same as double. And then we get the same thing as on the left. I think in all cases, this thing on the right gives the same results as the thing on the left. It's just a lot more work. Okay.
So there's a paper called that introduces decal call, which you might use.
Yeah.
But
Yeah, decal call would be super useful here. Yeah.
you get into trouble if you take more functions. I
Yes.
did a library which exactly does this.
Yeah, no, I haven't found a way to get it to work generically. I found in every particular case that I've needed, I can, finesse things to work the way that I want them to. But generically, yeah, no, you're right. You do need extra machinery here, and this is very difficult. Okay, so with that out of the way, let's talk about unique pointer. I'm talking about unique pointer because it exhibits a lot of the things, a lot of the semantics in C++ that we take as being very important and very core to the language. So I'll talk about data members first, then I'll talk about data accessors and member functions. I'll talk about non-special member function constructors. I'll talk about static members, for example, type defs. I'll talk about copying and moving, and then I'll talk about destructors. So data members is hopefully the easiest thing here. A data member is a capture, and I'm sure a lot of people may have assumed that I was going to do that because if it's a lambda, what do we have to work with other than captures? So on the top level, I have this unique pointer impl that takes in a t star, and then we capture this pointer into the lambda, and then we will do things with it later. But for now, I will say, yeah, that's my unique pointer. If we've only implemented data members and no accessors, that's our unique pointer. Nice. It's not unique. Great. Now let's talk about member functions. So again, remember, we are only using lambdas. The only thing we have to work with is the call operator. And so everything that I want to do needs to use the call operator. And so I should probably just take in a pack of arguments and decide what to do about it later. So that's what I did, basically. I take in a pack of call argument I take in a forwarding pack of arguments and I decide what to do with it later. I have this impl that will be something, and then I pass in first the data member and then the pack of arguments. And so, impl. Now let's talk about that. Yes?
The thing of sort of the premise of this is you're trying to get all the functionality, but it's not necessarily the exact same syntax.
No, not at all the same syntax. In fact, the syntax is going to work out to be horrible. But the point is to preserve ergonomics. And so, like, this whole talk is about preserving the ergonomics of C++ by doing things in a very bad syntactic way.
Okay.
But preserving not ergonomics. No one corrected me on that. Semantics. Preserving the semantics. The ergonomics will be terrible.
Yeah.
Sorry, that is what I meant. So we'll have this impl here, and it will be basically just an overload set. And the first thing that I'll add to it is the simplest member function, which will just be get. The get member function, it's not named get, but it will be get, and it will just return the pointer. Simple enough. Does anyone see a problem? I do. There's more than one get function. There's more than one function with no arguments in unique pointer. This right here is a function with no arguments, but how do we disambiguate with other functions, like release and like operator bool? I'm using tag dispatch. So I have this get memfun tag, and then I have the whatever get memfun tag. Every time you see anything ending in _tag, that's going to be just a unique type that will be used for this tag dispatching. Similarly, I'll have operator bool tag, operator star tag, and et cetera, et cetera. You'll see these throughout the talk. So what I'll do here is I will say, I want this overload to take get memfun tag. So now this is actually called the get member function. And now the Lambda itself needs to take a tag, and this tag will need to get passed into the impulse so that I can dispatch it. But now that I have that, I can make some space, and I can add an operator bool. That's nice. But that doesn't look like our regular operator bool. Does anyone notice a weird difference between this operator bool and a normal operator bool? Yeah, this isn't operator bool. There's no user-defined conversion functions. Like, I'm calling it operator bool, but that's only a name, right? It doesn't convert. You have to call it explicitly. It's a function. So we don't have any user-defined conversion functions with lambdas. But that's fine. We can get the same semantics. And we have gotten the same semantics. So now, let's create an int x, and let's take a const auto p is a unique pointer impl of the address of x. Yeah, that's not how you should write unique pointers, but I don't have any of the automatic lifetime management yet, so let's just deal with that for now. If I assert that p of operator bool tag works, it does. And if I try to get the pointer that p points to and then dereference that, that gives me 5. That also works. Okay, so I can actually differentiate between functions that have no arguments. Here's another function with no arguments. Here's release. Release is quite simple, the difference being it takes a t star ref. So this takes a non-const data member, effectively. And so this is a non-const function. And so if I try to call it, this will give me a compile error, because this is a const pointer, or a const unique pointer. I didn't particularly like the readability of that. The problem is, I don't look at that release function and immediately say, yeah, it's obvious that that's a non-const function. Not really. I mean, you have to notice that ampersand. And unless you're really reading, you might not notice the ampersand. And so I want to add something that will help readability here. I mean, well, this is only so much you can do, but I want to help a little bit. So what I'll do is first I will forward self along in the main impl lambda. So I take a class self, and then I take a this self ref. That's just forwarding self, and then I'm going to pass it to impl, and then later it's going to preserve the value category of self. So I do actually preserve the value category in a lot of places. I just missed that part earlier. But I did do it in most of the places. This to me still doesn't actually help in differentiating the non-const member functions though, so there's one more piece. I'll create this concept non-const. Pretty simple definition for a concept. And then in the release function, I'll just add non-const to it. And now I look at this and I go, yeah, that's clearly a non-const function because it takes non-const auto ref. All right, easier to read. Marginally easier to read. Let's show a few more functions. This will be reset. So here's another one. Reset is the first function that actually takes an argument. And the argument that it takes is the new pointer, and it'll be a default. This will just delete. Yeah, of course, unique pointer has a custom deleter, but this is slide code, so I'm omitting that so I can stay within the bounds of the time of this talk. We're just doing the regular delete on this pointer. And that's reset. We also have operator star. We have operator arrow. These work exactly the same to the implementations of operator star and operator arrow in a regular stood unique pointer. The difference being that they are not operator star and they are not operator arrow. You have to call them as a function. But other than that, it's semantically the same. Here's our first function that we need an explicit template parameter list. We take our non-const self, and then we need self ref as the first argument to this function to deduce the value category, and then self ref other to actually be the argument to be the actual parameter to the function. And I'm just implementing this in terms of release and reset. Quite simple. This is just a member function swap. Yeah.
Why didn't you do the non-const self on the previous one for release?
I did.
Oh, as a template parameter?
Well,
did I miss it?
Well, I just didn't have it in explicit template parameter list because I didn't need it.
Oh, okay. I see.
So it was non-const auto ref.
Yeah.
So it was just the, what do they call it? The terse syntax? Is that what they call it? And so I was just using that.
But here self is used in two different parameters.
Here self is used twice, so I need to write it.
It needs a name.
Yeah.
Thank you.
Yeah, it's because it's twice. Now that we have that, here's the general structure of the member functions. I have this unique pointer impl, which takes a t star, and then I capture this t star as a capture to this lambda. And then in here, I have self, I have tag, I have args. I forward along the self into the impl, I pass along the tag, I pass the data member, and then I pass the arguments. And then the impl is there as an overload set to grab all these things and to dispatch between all of the possible things I could send it. So it takes the self to deduce value category, or for other reasons potentially. It takes the tag, it takes the data members, and then it takes the args. And that's about the structure of data members. You also want a constraint on the call operator, but I'm just copying the body of the function, so that's a footnote. So that's member functions. Constructors, I want syntax that looks like this. I want unique putter of int, new int 123. I also want unique putter of int with no args. Why don't I just do unique putter is equal to unique putter impl? Because if I did that, I would only have one constructor. And I want more constructors. I want an arbitrary number of constructors. Well, but I could just do an arbitrary number of constructors with impl, right? I can have some constructor arguments. I can take a pack of arguments here, and then I can construct the captures based on what those arguments are, right? And so then I don't actually need to have anything outside the impl. This can entirely encapsulate unique pointer. So then, if I create a unique putter of int with no arguments, and if I create a unique putter with null putter, they're different types. That's not a good thing. So I'm going to consider this, no, you can't do that. I need unique putter impl to have a non-generic call operator. Because if it's generic, you end up with a different type of the internal lambda every single time you instantiate a different set of constructor arguments. And that's not okay. If you construct a type from different sets of arguments, you should expect those to be the same type. And that's part of maintaining C++'s semantics that I care so much about. So I'm going to say that's not okay. What I will do instead, I'll say unique putter is an overload set that will take, first there's a nullery lambda that defers to unique putter impl. There's another one that takes null putter t, and there's another one that takes just a t star. And these all call the non-generic call operator of unique putter impl. And so that's constructors. Now I can create a p1 and a p2 from different constructor arguments, and I can make sure that they are actually the same type. And that's a good thing. I want them to be the same type. I'm going to consider static members to be kind of the same thing as constructors, because I mean, you know, philosophically, a constructor is kind of just a static function that creates your type, or it creates an object of that type. So I'm just going to have them as part of the same overload set. And it'll make sense syntactically as well. It'll make things a little bit easier in the mess of things not being easy. So I'll take this pointer typedef tag. So this is another one of those tag types. This will grab the pointer typedef, and it returns the type identity. Here's another one. It's an element type typedef tag. So this will return the element type. With a normal unique pointer, you can call whatever the type is : pointer, and that will give you the t star. But here I can't do that, so this is the next best thing. But once you've done it, you can just call unique putter int with pointer typedef tag, and that will give you the typedef called pointer. And element type is going to be the same thing. And just to ensure that they work, I'll bring back my type of alias, and yeah, I'll ensure that they work. And they do. And the same thing would work with a static member function, right? If I wanted a static member function, I would just create some other tag that does the thing that I want it to do, just to disambiguate it from possibly being a constructor. But otherwise, yeah, seems like it should work. Copy and move is a little bit more complicated. Let's start off like this. Let's start with assignment. If I have these two unique pointers and I try setting p2 equal to p1, what happens?
Lambda closure types are not assignable.
Lambda closure types are not assignable. And from the standard, actually, it has a deleted copy assignment operator if the lambda expression has a capture. If there's no capture, they actually are assignable. But because there's a capture, they are not assignable, and we only are using captures if it's a class type, because that's how you emulate classes. And so, yeah, it's always deleted. But what we can do is have this operator assign tag. Again, I'm introducing new tags, and here's another function. And yeah, the syntax is terrible, the ergonomics are terrible, but it does the same thing. This is a move assignment operator. Notice it takes a self-ref as the first parameter to the lambda itself, and then as the actual first argument to the function, it's self-ref other, it's an R value reference. And it's just implemented in terms of release and reset. And that's operator assign. That's a move assignment operator. It's an ugly move assignment operator, but it's a move assignment operator. Semantically, it does the right thing. If I call P2 operator assign tag move of P1, yeah, that works. Like, it clears the pointer in P1 and gives it to P2. And that's exactly what I want. And if I try to do it without moving P1, it gives me an error. And that's perfect. That's assignment. That's the easy part. The hard part's construction. So first I'm going to define this unique putter underscore t alias. This is going to be the type of the lambda that is our unique pointer. See, we had this problem here using only lambdas. With a regular type, unique putter of int, for example, is both the symbol that we use to construct values of, or construct objects of this type. It's the symbol that we use to call static member functions, but it's also the symbol that we use to denote the type itself. We can't do that with lambdas, so we have to separate them. And that's what I did here. I have unique putter underscore t is just that type itself. We're going to need that because I'm creating two new constructors. The first constructor here is const ref, and it's just deleted. I could have left this blank, but I want to make sure that when I'm reading this code, it is explicitly deleted. So I could have commented out the whole thing. I could have deleted it, but I decided to do it like this. And then here's my move constructor. It's implemented in terms of release. And this is a valid move constructor. And notice, this is going to be an explicit move constructor. And by that, I mean, in order to move construct, in order to create this P2, I have to call unique putter of int move of P1. But once I do that, it works. And if I try to do it without moving P1, of course, it doesn't work because there's a void return type. I went / deleted inside of that constructor, so it just doesn't work. If I try to just move P1 into P2, or I say auto P2 equals move of P1, or if I say auto P2 equals P1, what happens? So what happens is they do a shallow copy. And if there's one thing we don't want a unique pointer to do, it's a shallow copy. It's one of the core things of unique pointer that makes it important. As per the standard, in fact, the same clause as before. It has a defaulted copy constructor and a defaulted move constructor. In all cases, what if I want to inject some user-defined behavior into the move constructor? Can't do it, right? You need a class for that, because all we have to work with are fundamental types and lambdas. So we can't have any user-defined implicit copy and move operations. We have our explicit ones, but we don't have our implicit ones. Yeah?
If you had a lambda that had a capture that's not copyable.
You're getting ahead of me. I'll get there. Okay, so the first thing that I tried to do, actually, is to create this move wrapper. And I thought, I'm going to wrap a value. I'm going to construct this value. I'm going to delete the copy constructor. And then I'm going to create a move constructor that creates a value that just exchanges the other value with a default constructed t. And I thought that's fine. And then I sat there and I thought to myself for a little bit. I actually have a picture of me thinking to myself. And I thought, I don't really like how this is going, because this might not work in all cases. Like, this might not be what I want for every move constructor, right? And then I went down the rabbit hole of, well, how could I do this more generically and whatever? But it would be a lot of rule breaks. And I thought, no. I need to get back to the drawing board. I want to implement things as minimally as possible. And the minimal thing that I can do is a struct no copy. And I think the simplest way to make a type that is not copyable is to delete the copy constructor explicitly in a struct. I don't know if you can do it with just lambdas and fundamental types.
Well, lambdas are not copyable, so you could make it the lambda data member of the...
No, lambdas are copyable. Lambdas have a...
Yeah, okay, they're not copy assignable.
No, they're not copy assignable, but they are copy constructible.
Yeah.
And so the only way to delete a copy constructor is to explicitly delete the copy constructor in a struct. And yeah, this is 3 rule breaks, and I don't like that. But this is as minimal as possible. With using a move wrapper, who knows how many of those move wrappers I would have to write. So this is only 3. And what I'll do is I'll add another capture, just like you were saying. I'll add another capture that's this no copy. And other than that, yeah, that's how you do it. I'm making it underscore because it doesn't matter what it's called. And now, if I try to do auto P2 equals move of P1, it's an error, as well as auto P2 equals P1. So this deletes the implicit copying and moving. If I have a function that takes a unique pointer and then I have a unique pointer, how do I pass it to that function? Well, I have to do it explicitly. I can't just say f of move of p1. I have to say f of unique putter of int move of p1, because I have to construct explicitly. It is not move constructible. Not in the actual C++ sense, but it is semantically move constructible in the sense that you can write something to do the move construction. And let's say inside f, I wanted to forward it to a g and, carry on the chain. And now let's say f is generic. Now I've run into a problem. The problem is, how do you generically, explicitly move construct? And the way that I solve that problem is by writing a new tag, of course. Everything is more tags on tags. And then for unique pointers specifically, I wrote this unique putter factory. I set it equal to 0, effectively just a declaration, no definition. Inside of the overload set in the implementation, I wrote another function called factory tag, or that is called factory. It takes this factory tag. Now, this will not collide with a member function called factory, because that tag would be called factory underscore memfun underscore tag. So to preempt things that people might say, this will not collide. And then this just returns whatever the unique putter factory is. I'm passing it 2 template arguments because at least one of them needs to be dependent on the call operator itself. And now I'll create my unique pointer overload set, and then after that I'll finally specialize my unique putter factory to be equal to that unique putter. So that'll be the factory. I'm calling it the factory. And now I press something. Now I have the solution for this problem, which is to say in G, I can just call factory tag on P and then pass in move of P into that. And that's an explicit move construction that's generic. And if I want to make sure this never happens at runtime, I can have a decal type. And then, I have so many parentheses here, I might as well have been writing Lisp in the first place. So that's copy and move. But it doesn't come for free. It does come with 3 rule breaks. Namely, no copy the struct itself, as well as its 2 constructors that I do have to name in the struct. So that's 3 rule breaks. Now let's talk about destructors. Here's what I want to do. I want to capture the data, and then I want to make a destructor for that capture. There are 2 problems here. One might be obvious, the other one's not obvious. I'll go through the obvious one first. The obvious one is that I can't call any user-defined code, any arbitrary user-defined code at the end of a scope. Now, what I could do is, I need to create a destructor for that. What I could do is I could make the Lambda return a function that is effectively the destructor, but that changes the semantics of C++, because that means that it won't get called at the end of a scope, and by C++ semantics, it needs to be called at the end of a scope, otherwise you don't know what's going to happen. Yes?
Cap2 can't depend on Cap1. There's no defined initialization on that.
Right, that's the second problem.
Right.
Yeah. So that's the second problem. But I just wanted to go over the first problem first,
okay.
Which the obvious one is to say that you can't write arbitrary user-defined code to run at the end of a scope, unless you're actually writing a destructor, which if you're using just lambdas, you aren't. The other problem is undeclared identifier cap1. Like, you can't even do this regardless of what the function is, because you can't use a capture inside another capture because the order is not defined. But the actual reason that I found in the standard is to say that the init capture inhabits the lambda scope of the lambda expression. Digging deeper, that means that a lambda expression e, etc., the scope starts immediately after the introducer, which means that the scope of a lambda capture happens after the lambda captures. So you cannot use a capture inside of the lambda introducer. So here's our restriction. I talked about this. This was the first problem. We don't have any user-defined destructors. It's a lot of problems. I'm going to solve it like this. I said I didn't want to make some generic, function calling thing, but here I think I actually have to. Here I'm taking a non-type template parameter for the destructor. I'm wrapping a value. I'm defaulting the copy and move operations, and I am calling the destructor at the end of, or I'm calling this destructor function in the actual destructor of this struct. And yeah, that's a big rule break. Like, that's 5 rule breaks, because the struct itself and then the 3 constructors and the destructor. This is as minimal as I could get it. Because to maintain C++'s semantics, you need to have code run at the end of a scope that is potentially arbitrary code. Otherwise, you really kind of destroy the semantics that we have in C++. And I wasn't willing to do that for this talk. So the way that I'll implement this for a unique pointer here is I'll write this destructor. It's going to say if p, delete p. Very simple destructor. I'll make the data type be the destructor wrapper for a t star, comma, destructor. Now, I would have loved to have the destructor be a separate capture, but it can't be. It needs to wrap the other capture. And that actually has a lot of implications for implementing other things further down the line that I actually don't have time to talk about in this talk. But the fact that you have to wrap all your data means that if you have multiple data members, you need to wrap everything inside of a tuple, and it ends up getting very messy very fast. But here it's very simple, and it's slide code, so I'll keep it simple. Then the capture is going to be, instead of underscore pointer, it'll be underscore data. I'll construct the data, and that's about it. And now I have a unique pointer that works the same way that a C++ unique pointer works. And I've done it with almost only lambdas, 9 rule breaks. So struct template destructor wrapper. So I mean, because realistically, the question wasn't, the goal of course was to write everything with only lambdas. But with the understanding that there are going to be places where we cannot use lambdas, and so my goal is to determine the minimum number of rule breaks. And I think 9 rule breaks so far is pretty good. I said so far. The last section of this talk is going to be more features. Let's propagate, copy, and move. Let's talk about member function templates through the lens of tuple. Let's talk about the equality operator also through the lens of tuple. Let's touch on reusable storage. Let's touch on the range-based for loop. Let's touch on declarations and translation units. And then finally, we'll end where it all began in the main function. OK. Propagating, copy, and move is a problem that happened when I was implementing tuple. So I have an int, and then I have a unique pointer. If I want to move generically, how do I move generically? They have different syntax. And so I need to write something that dispatches to the different syntax. So I've done this in a few different steps. I have maybe copy construct, which if auto decay of t is a valid thing to do, as in if you can just do a regular C++ copy construct of this thing, then just return that t. And because I'm returning decal type auto, this will actually return the reference. This will be 0 overhead, I think. I don't care about the runtime, obviously, as you can tell from all this boilerplate that I write. Otherwise, we want to dispatch to this factory tag and then pass in the t. So this is going to be an explicit copy construct. I'll do the same thing for move construction. The difference is I just want to make sure that I don't match against a const t ref. Because a const L-value reference can match against a tref, and I never want that to happen, so I'm going to require that that never happens. But otherwise, this works exactly the same. If auto decay of move of t is a valid thing, then I want to return move of t. Otherwise, I will do this explicit move construction. It's messy, but it works. And so now if I want to do a generic move, yeah, I can just dispatch to this maybe move construct. And it does the right thing every time. I think, for some definition of every time. Then I'll have this maybe forward construct that either dispatches to maybe copy construct or it dispatches to maybe move construct, because you may need to do things that you don't know necessarily what you want. Basically, if t itself is a reference type, that means we have matched an L value, and so we need to pass this into maybe copy construct. Otherwise, if t is a value type, that means we're going to pass it to maybe move construct. And that's dispatching for maybe forward construct. And the final piece on top of this will be a lambda called construct, rather a lambda template called construct. It will take a forwarding parameter, returning decal type auto, and it dispatches doing a few different things. The first case is that u and t are the same type. And if u and t are the same type, then we will just maybe forward construct the u. That's the simplest case. The next case is if we are able to construct a t directly from a maybe forward constructed u, then do that. Otherwise, call the factory tag on the t and then maybe forward construct the u into that t. Okay, it's a bit much. Hopefully you only have to write this once. Hopefully no one has to write this ever. So I'm going to talk about member function templates now that we have that out of the way. I'm going to do that through the lens of tuple. So tuple here, I'll have this tuple impl in the same way that I have the unique pointer. And this will take a pack of t's, by value, because we don't know how many things, we can't necessarily specialize this for different numbers of arguments. It has to be a pack. We'll have this impl. We don't know what the impl is yet. I'll get to that later. We will have some lambda that captures all the members by a pack capture with an initializer. This is where I need maybe move construct. This was the place that actually was the impetus for me to write it in the first place. This lambda is going to have all of the same sort of parameters that we had in the unique pointer. So the general scaffolding will be the same. The main difference is that the order that we pass the parameters to the impl is going to be different, but that's only because from the perspective of the impl, for each of its overloads, all of the arguments will not be variadic, but the members will be variadic, so they have to be after. So we'll pass in the forward itself, we'll pass in the tag, we'll pass in the arguments, and we'll pass in the members. Great. I will talk about two member functions of this tuple, exactly two of them. One of them is a member function that does not exist in the standard, that is tget, the template get function. Obviously, it's not called tget, it would just be called get, but I do need to disambiguate this from the regular get. And so what I would love to do is I want to pass in tget memfun tag of, for example, 0, and then I want the size t to be deduced as 0, and then I can use that in the body of the function. That doesn't work. Does anybody know why? Shot in the dark, I mean.
Tag?
So, sorry?
I didn't know you could make templates for your tags can be templates.
The tags can be templates.
Yeah.
The problem is that we have very limited template argument deduction. And I have a very simple example to show why. Here I have a template tag. This is a very simple template tag.
Right.
It's just, as simple of a template tag as you can get. I have a function that takes a template tag of t.
Let's deduce it two things.
It tries to deduce int, and it can't. How would it possibly deduce int? It's an alias. You can't do that with aliases in C++. So that ends up being, a little bit of a problem for the member function tget. So what I ended up needing to do instead is to have this tget memfun tag f as a lambda. It returns the size type I, and then I have my tget memfun tag, which again, I use that thing that we used at the beginning of the talk, this decal type auto, just grabbing the type of the closure object itself. But now the problem is I can't use this template tag in the way that I wanted to, right? Because I wanted to use it as tget memfun tag of whatever I is, and then I wanted to match that I. I wanted to do the pattern matching that is template argument deduction on that I. You can't do it.
Take another argument.
Sorry?
Could you take another argument?
How would another argument help?
You could do a case statement. I don't know.
At compile time? I don't know. I mean, I'm sure there are things down, in the pipeline in C++ 26 or 29 that might help here. The way that I decided to do this, I'm not saying you couldn't do it a different way, but the way that I decided to do this is just to take a tag and take it just as a tag. The problem is, though, if you write it just like this, everything will match against this. And I don't want every tag to match. I need to restrict it, so I will constrain it. I will say that I'll have this constraint, I think, constrains 4 things. It constrains, first of all, that you can construct this tag at compile time. It constrains that you can call the call operator at compile time, that you can take the result of that and pass it into tget memfun tag, and that you end up getting back the original tag that you started with. So it's quite the loaded constraint, and it does all the things that you need it to do. The only other thing is, just to make sure that the value is in the correct range. But now that we've done that, okay, now this is actually properly constrained, and now we're able to add other member functions to this. And this is the whole idea I had with member function templates, that if you need member function templates, you need some way to not have it be the last thing in the overload set, right? Because you might need multiple of them. So if we weren't able to do these constraints, then yeah, that would be a problem. But I think we are. So now actually let's implement this tget function. This is going to be a fun exercise in recursive lambdas. Here is the scaffolding of the recursive lambda. It's going to take in a size ti as a template parameter. That size t is going to be defaulted to just the value of whatever is in the tag. it will take the first member, and then it will take the remaining members, and we'll kick that off at the bottom with a forward like all of the members. So we'll pass in all of the members, we get it started. And there's two cases. First case is we're down to 0. If we're down to 0, we just return the member. If we're not down to 0, we recurse. I tried to figure out a way to get this to work with a fold expression, but I was not able to do that. The reason being, the thing that I talked about in the beginning with Daisy Holman's enumerate pack, the amazing cute trick that she came up with, you need to match a std index sequence, and you cannot match any template arguments because we're using only aliases. So even if you have a std index sequence, even if I created an index sequence, the index sequence would still be some alias to a lambda type, and it still wouldn't match. So I wasn't able to figure out a way to make this be a fold expression. I would love for it to be a fold expression, believe me. Richard, were you going to say something?
No, I found nothing. I thought there was, no, it's good.
Okay, cool. Yeah, so that ends up being the problem. So whenever I need to write something that would be one of those immediately invoked fold expressions that I would have written in C++20 in regular code, because we're using lambdas, and lambdas have to be, or we have to grab the name of your type, you have to take an alias because it's an unnameable type. Because of that, we just can't do any of the fold expression, the nice fun tricks that I would love to do. So we're stuck with recursion. But in C++23, recursive lambdas are nice, so it's not the worst thing in the world. And that's the template get. But you may be thinking, well, we don't have a get member function in std tuple. Yeah, okay, we have free function get. And so I'll say the free function get just dispatches to the template get function. And then there's a problem, because std get has overloads for different things. Std get has an overload for std array, for std pair, for std tuple, for others. I think there are others. And that's an issue because with lambdas, you cannot define the same name multiple times for different purposes. You can't do any sort of overload sets that are extendable. There's no extendable overload sets directly. Yes?
I've been thinking about a way that you could do your tag. So your tag maybe could be a function type where, like, for example, one of the parameters is a lambda type.
Okay.
So that would make it unique. And if one of the other parameters of this function type is the template parameter, you can deduce through a function type. So maybe
through a function type, like a function pointer?
Yeah, you can make an alias to a function. It doesn't need to be a function pointer type. It can be a function type.
But in doing that, I've created another rule break because I don't want to use functions.
Not even function types?
No, that would be a rule break, as per the rules that I've set up. Mm-hmm. And I'm trying to figure out how to use as few of those as possible. And so because I was able to figure out a way to do it without writing a function type, I would prefer to do it that way. So no, I'm sure it would be better. I'm sure the syntax would be a lot nicer. But I mean, this whole talk is about exploring the limits of what we can do without those things. So yes.
Yeah. I'm wondering if you could have used a variable template instead of the variable that because the problem is you've got a named object that you need later.
Yeah.
Could you make that instead of just an object, a variable template, which would let you get a selector for the name of it?
I think you're right. I must have been a little short-sighted when I wrote this part.
Oh,
because,
like we've only some of the stuff with variable templates is like brand new in terms of being.
Yeah, no, that is a good point. And now that you say that, I'm like, yeah, I didn't even try that. But luckily, I was able to come up with a way of doing this without breaking a rule. Because it would have been very embarrassing if I had to break a rule here, and then I have people in the audience saying, well, no, you didn't need to do that. Like, that would have hurt. But so far, that hasn't happened. We'll see for the next 10 minutes. But okay, the other function for tuple that I want to talk about is the equality operator. So for the equality operator, this is inside of the tuple implementation. Again, I'm using operator equals tag. And so this is going to be another recursive lambda because, again, well, as far as I'm aware in what I've done, I can't do that fold expression. I would love to figure that out later if possible. So the way that I do this is if I is at the end, then just return true. Otherwise, let's just walk pairwise. And so I'll say, I want to grab the left-hand side and I want to grab the right-hand side. I need to check for the correct operator equals. Because if it's one of these weird class types that I've written in this talk, then I have to use operator equals tag. And so I have to use operator equals tag. And then I can move on to the next thing by recursing, and this, of course, short circuits. Otherwise, I do need to use the double equals, and this will also short circuit and then move on to the next thing. So that is operator equals. And then here I'm going to write a global operator equals that just defers to the member function operator equals. What's wrong with this?
That's a function.
It's a function. No, I can't do that. So there's no operator overloading, like at all. I can't do any operator overloading with only lambdas. I kind of had that implied in a few of the other conditions, but this one explicitly says it, no operator overloading. What we can do is we can have an op equals and we can just pass it the things and it can do the right thing. Yeah, sure, that works. It doesn't have the same syntax, but it has the same semantics, and that's what we're after. For reusable storage, so I'm talking about some types, like optional, variant, and expected. We need some way of reusing the storage inside of the Lambda. And so what I want to do is capture an array. Here's a clause from the standard that will be useful in about a minute. An init capture without ellipsis behaves as if it declares and explicitly captures a variable of the form auto, whatever you wrote in the init capture, semicolon. Keep that in mind. I want to create an array type, and I want to capture that inside of my Lambda. Is this valid C++? It is not. I probably wouldn't show it otherwise. Because it's equivalent to this. And this is obviously not valid C++. You can't deduce an array type, like a C array. Like you just can't. This just isn't valid C++. And so from that clause in the standard, that sort of translates that capture into this line. And you cannot do that. So here's a restriction. We can't have any array captures. So I have two options of what I thought of doing. This is the first one that I went along with for quite a while until I realized the fatal flaw. I went with a line storage T. This used to be in the standard. It's no longer in the standard. Yes?
Just a question. Could you use a lambda and have an array with a static storage duration in it and return it and use it?
Potentially. I would be concerned that if we called the same thing twice, then it would be reusing the storage. And we can't have it reuse the storage.
But if we make it as like an anonymous lambda that every time we call it, it should be in U.
Well, no, not every time you call it. Every time you write it, it's different. But every time you call it, it's still the same one.
If I make an alias of the lambda, which
yeah,
has a static storage duration array inside,
okay,
and every time I use it, that should be in U. No?
No, okay. I don't think so. Maybe. I don't think so, though. So what I wanted to do is this, and this is a lot of what I went with, this align storage T. And then I found a fatal flaw, and I decided I actually need to try variadic union. And I didn't actually complete this yet. This is not a complete bare bones implementation of how you need to use variadic union in order to implement a std variant. And that is how all the standard library implementers do std variant. They use some sort of variadic union. Why? What's wrong with the left-hand side? It doesn't work at compile time, because we need reinterpret cast. But the right-hand side is able to work at compile time. Now, theoretically, it's able to work at compile time. I know that because the standard libraries do it. I haven't figured that out yet, but I know that it's possible. So I'm going to say that it's possible. And I would prefer to use the right-hand side, even though so far in my own implementation, I have implemented std optional using the left-hand side. And so there's an unavoidable rule break that I have here, which is, I don't know how many, because I don't know how many I'm going to actually have to define for variadic union, but it is another set of rule breaks that we do need in order to implement std variant at compile time. Yes?
I don't know if this will work. It's a crazy idea for storage. Can you use an oversized bit field type? Because they exist.
An oversized bit field type? I don't think I know what that means.
Int colon n times 32.
You would need to write a struct for that.
Do you? Or is it a
yeah.
type?
No, I don't think it's a type. I think it's only a field.
Data members of
yeah, it can only be a field of a struct.
Okay.
So I mean, we could have a rule break there, and maybe that would be fewer rule breaks than a variadic union. I don't know, because I haven't finished going down this rabbit hole yet. It came up too recently to when I'm standing here right now. Okay, last couple things in this talk, I'm going to mention the range-based for loop. In the standard, it changes the statement that's seen first into all of those statements that are seen later. The main parts that are really important here are the begin expr, end expr, and then all of the things that we do to begin and end. The reason being that we can't call these operator overloads. So we're going to need to do different things. But assuming we have compiler support to desugar all these things, then yeah, we can do that. Like we can create a vector event, and then we can create the begin and the end using the member function begin and end with the memfun tag, assuming that the compiler desugars that. And arguably, if the compiler does not desugar to that, we'll write it ourselves. Because as I said at the beginning, I don't care about the ergonomics. And so we're able to do it. And then in the for loop itself, we'll need to use op equals, and then we'll need to use begin of operator pre-increment tag that's equivalent to ++ begin, and then operator star tag is star begin. And yeah, we got range-based for loops. So we can do it. Declarations and translation units, that's a bit of a problem. Let's say I want to declare a lambda somewhere, and then I want to define a lambda somewhere else. You cannot do that because you can't name the lambda type. It is unnameable. Lambdas have external linkage. If you are able to use a lambda in 2 different translation units, it is actually 2 different lambdas. And you have, I think, depending on how you do it, an ODR violation. Is that what we talked about yesterday? Right? Yeah. So, yeah, we don't really play well with translation units. Really, the best we can do is either a Unity build or header-only code. So, yeah, we don't really play nice with any of this sort of thing. So we have these restrictions. We have, we can't separate declaration and definition. And on top of that, we can't link things across translation units. And maybe those are 2 sides of the same coin, but I did want to spell them out explicitly. And then finally, the main function. As per the standard, a program shall contain exactly 1 function called main that belongs to the global scope, so we're off to a bad start. It is implementation defined whether a program in freestanding is required to define a main function. So, okay, a conditional rule break. Main in hosted environment needs to be a rule break. But hey, if we're in freestanding, maybe not. So maybe this will make me switch over to freestanding at some point. All right. So in conclusion, lambdas are very powerful in C++. As I've shown, there are a lot of things we're able to do. But there are a lot of things we're not able to do that we take for granted. Like, we can't have any implicit conversions. And the way that we came across this in my talk was with base class slicing. But there's other ways that we come across this, like conversion operators, which I'll mention later. We can't have any member type defs. This is very important for non-deduced contexts, for example. We can't have a compiler select the overloading. We have to do it ourselves. We can't have any user-defined conversion functions. We can't have any user-defined explicit copy or move operations or any user-defined destructors. There's very limited template argument deduction, unless there isn't, and let's talk about that later, because that was a good suggestion. We can't have any directly extendable overload sets. We can't have any operator overloading. We can't have array captures. We can't have separate declaration and definition, and we cannot link across translation units. So it's a long list. And obviously, this is not the complete list. We came across some unavoidable rule breaks in this talk. First of all, the struct template type identity. Sorry, the type identity must be a struct template before C++26. In C++26 with P2996, we can actually cross this off the list. So looking forward to that. We need to create this struct called noCopy that ensures that our lambda types do not get copied and moved when we don't want them to. We need to create this struct template destructor wrapper just to ensure that we are able to get destructors to be called to maintain C++'s semantics. We probably need this union template, variadic union, in order to create some types that work at compile time. And we need the main function to be a function in hosted. But are there others? And realistically, I went into this thinking that this would be a closed set. And I came out of this realizing that the standard library is huge. It's a wonder that it took me this long. But lambdas are very versatile. That's a very important takeaway. They can replace most classes and functions. And I hope I've shown that throughout this talk. But of course, not all of them. One very important takeaway that I just learned is that the standard library is huge. But most importantly, play around with your code. You know, like this is just an exercise in pushing the boundaries of what we're able to do with the language, and you know, to see what pops out of it and to see what we learn from it. I know I learned a lot from doing this, and it's been a very good time. So my code is available at my GitHub. It is incomplete, but it is there. Thank you very much for listening to this talk.